recording going? Okay, so as we look at Module 5, you're going to notice that it's called dimensioning, okay? And dimensioning really kind of puts the, if you would, final touches on our designs so that they can be released to production, okay? The dimensions tell the person who's making the part what are the sizes and what are the special things you need to take in consideration as you make this so that it functions in its final form, okay? This is probably the most important thing that you do as designers is you create the drawings, and ultimately the dimensions are part of that. So you'll notice here that we have drawing borders here, okay? We're going to be downloading WCTC drawing borders that we're going to be using on our prints, okay? When you go to a company, they're going to have their own drawing borders, okay? So we'll talk about the elements of that and what makes those different. You're going to notice that we have 2 sessions here. The first session we're going to be doing this evening, and we're going to be first going over the basics of dimensioning, which are going to be out of chapter 11 in our tech drafting book, okay? We're going to get to know the rules. We're going to give you things that you can look back to in order to know if it's the appropriate, way to dimension. As I think I've mentioned in the past, when we're looking at the ANSI standard and how to lay out parts, how to dimension, how to properly put things in place, we're learning a communication tool, if you would, kind of like learning the English language. This is the language, the graphical language that you're going to use then to convey your ideas. So being able to properly dimension, being able to properly tolerance, being able to lay out your drawings appropriately. If you don't do that to the ANSI standards and using the rules that we're going to be learning here in this chapter, okay, and again, having something to go back to verify things, then you're always going to get questions and there's always going to be things to go over. So it's super duper important. The most important, I believe, the most important thing that we do as designers and engineers, okay? The second time we're going to be together, we're going to be continuing on. I have 2 assignments for you. So this evening, we're going to be working on a little bit later. We're going to get started on the AutoCAD stuff this evening. So there's going to be some practice problems we're going to be doing. And then, and those are going to be associated with assignment 5A and 5B. So total, I think there's 8 drawings with borders and dimensions that you're going to be handing in for Module 5. And we're going to kind of get you started this evening and the next time that we're together. And then, like I said, usually like to try to have our 3rd meeting during the week here as a work time. And I anticipate that this week like normal. Okay. So let's look at session number 1. Okay. So as we're looking at the learning plan here, you're going to notice that the agenda, first thing we're going to do is we're going to look at chapter 11 in our, I call it the tech drafting book. That's Gajewski. That's the author. And we're going to be looking specifically at, like I said, kind of rules of dimensioning, getting us used to how we're supposed to do things. Okay. Then what we're going to do is we're going to shift gears and you're going to apply those dimensioning rules, but we've got to set some things up in AutoCAD. So we are going to have to look at the dimension style manager settings and kind of get things in place for us to use. We're going to be downloading the WCTC borders here so that we can also use those and incorporate those into the assignments that you're going to be doing. And then practice problems for Module 5. We're actually going to be pulling up 2 familiar parts. You already did the drawings for the saddle bracket and the anchor base. Okay, so you've already done the 3 views. Now what we're going to do is we're going to put those on a border and we're going to dimension it. Okay, and we're going to be seeing how that we do that. So that's going to be a nice introduction for us. So my plan, this is our agenda. We've got quite a bit to do tonight. So we're going to get started here with the chapter 11. Dimensioning rules, if you would, in our tech drafting textbook. So I am going to click on that PDF and we are going to use this to kind of guide us through the chapter. You're welcome to open up to chapter 11, but I kind of have all the illustrations here for us on the PowerPoint. So whether you want to follow along on the PowerPoint or open up in the book, feel free to do so. If you are wondering about rules and examples, my whole objective here is it's not going to all sink in right away. It's going to take some practice, but I want to be sure that you have a resource, chapter 11, to go back to and know what's in there. So then you can check, like, how do I put a radius on again? Or how do I dimension? Where do I put my dimensions? And there's a lot of great examples in there. Okay. So that's what we're going to touch on here. So Why is dimensioning important? First and foremost, it communicates the requirements that we need for that part to be made properly and to ultimately function correctly in its final form. Okay. So our dimensions not only give us size, but they also give us tolerance, which is the limit for which the part has to be made within. We will continue to talk about tolerances throughout the program. So we're going to touch it here, okay, and in tech drafting, but most specifically in this module, we're going to be focusing on like how to get those dimensions in place, first of all. And then module 6, we'll do a little bit more with tolerancing, okay, as we look ahead. So we also have to make sure that this part can be manufactured. So part of if you're in the program, and you're kind of moving along, you're going to notice that you have 2 manufacturing classes to take. There's cold processes and there's hot processes, okay? And those 2 classes are not to make you machinists or welders, okay? But what it's supposed to do is to give you experience doing those processes so you can make better decisions for your drawing, because the way that you dimension, the tolerances that you put on, and the types of features that you design, if they can't be manufactured, then it doesn't matter how awesome it looks on paper or on the screen. If it can't be made, it's not usable. Okay. So we want to make sure that you're taking that into consideration. And then also the dimensions that we put on and how they're dimensioned and toleranced, it's going to determine the cost of that part of that feature. So we want to be sure that we are optimizing that so that it is cost effective, so that the parts can continue to be made, so our employer can stay in, in business, so that we can continue to get a paycheck, quite honestly, okay, and that they continue to make the money they need to stay viable. And that starts here. If they're manufacturing a part, it starts with the drawing. Okay, it's an important job that you guys are doing. It's not just, I'm just going to make a drawing. It's a big deal. Okay, it's a big deal. It drives the cost in that company. Now, 3 aspects of a good drawing. First of all, good techniques in dimensioning. And that's what we're going to continue to work on, not only starting here in tech drafting, but continuing in the courses as you go along in the program. We're going to continue to touch on this. I'm teaching the advanced SolidWorks class right now, and we're still dimensioning. We're still tolerancing that, because that's going to be a main part of your job when you're out in industry. You want to make sure that you place the dimensions appropriately. So those are things that we're going to see here in chapter 11. What are the best ways to, and what are the rules of, okay? And then what dimensions you actually choose. That's going to also help to dictate, how the part is made, and then ultimately the process that's going to be used in order to make it, okay? Now, tolerances, just a little bit on tolerances here, at least starting out and looking at a title block. So a tolerance is the total amount that a feature on an actual part is allowed to vary from what is specified by the drawing or the model dimension, okay? So if I peek back up here, a dimension is going to be a number that is between 2 lines that have arrows that are specifically giving us, in this case, if we look at this 274 dimension, the arrows go from one end of the part to the other. So it's giving us the overall length. Okay, that's the dimension. And notice there's a single number there. Okay, now that single number only gives us, if you would, what we call a nominal value. This is like the middle number that we're hitting. If there is no specific tolerance in back of the dimension, which we see here, okay, then we go to our title block tolerance to determine what the actual applied tolerance is on there. And like it says here, the tolerance is the total amount of variation that we're allowing on a feature for it to function properly in its final state. All right. So if there's not a tolerance specified, or there's only one number in that dimension, there is a tolerance. It just defaults to the title block. Okay. Now, title blocks will have different tolerances. Number 1, based on the units that we're dealing with. So for inch, for instance, there's going to be a set of tolerances, and it's going to be on an inch border. All right. If we're dealing with metric units like millimeters, then there's going to be millimeter tolerances, and there will be a metric border. So you're going to find that when we go to download the borders, there's going to be inch borders and there's going to be metric borders. Okay. So depending on the units that you're working with, you're going to have that. And then in the title block, and I'm looking right here because I can see that this is where that's at, they're going to give us what we call the standard tolerances. Now, a company, you're going to notice that you're going to see that you usually have a company border here. On our WCTC borders, we have our WCTC, logo, and it's going to have that information. But when a company has their logo, and there's usually some sort of a statement on there that the information on that drawing is for the sole purpose of, and it really identifies ownership of that drawing. And it's against the law to actually use it for any other purpose than what that company is going to use. I used to do a lot of training at Kohler Company when I was working at the other college that I worked at because it was up in that district. And they were very strict on materials that I could take out of the company. They would search my car when I would leave to see if I had any parts or any drawings. And I'd have to, sign off and say that I wasn't going to share any secrets because that's their business. That's their bread and butter. And they don't want anybody to know about that. So companies hold that sacred, if you would. So a title block is always going to include company information and any disclaimers, if you would, of ownership. You're also going to see here these tolerances, okay, these standard tolerances. So you always look to the title block. Once a company identifies those, they can never be changed. Those are part of the title block. So if on a drawing, you're like, I don't want to use the title block tolerances, I'm going to change those in the title block because all of my two-place decimals are going to be something else. You can't do that, all right? Then if you don't want them to default to the title block, then you have to actually put specific tolerances in back of the actual drawing. You never change a title block standard tolerance, okay? So that's kind of the rule. Among other things that we see here on our title block are going to also be the part number, the name. Usually you have the person who created that, the date that it was created, material that's required for it, and then any other information that is deemed important. So these can vary a little bit, but those are kind of things that we're going to be looking for. And especially when we look what we call the title block tolerance. If there's no title tolerance immediately in back of the dimension in the drawing, it defaults down here. So that means every dimension has a tolerance. Okay, every dimension has a tolerance. Geometric breakdown here, it's just kind of showing us that when we're putting parts together here, it's usually a compilation of different types of shapes. So whether it's a cone or a cylinder, we've got a prism, we've got, this block shape here. And as we put those things together, we then have our parts. So that's how we build those. Lines used in dimensioning, okay? We're going to have dimension lines, extension lines, and then like it says here, center lines. Center lines are considered part of dimensioning only because it is where we're going to, if you would, grab a location to when we are trying to identify the center of something, especially a cylindrical feature. When we are making them using tooling in the manufacturing environment, the spindle center we can identify, and we know where that is in space. So we use that spindle center or the center line of a cylindrical feature if we're making a hole, for instance, or a bore, and that is identifiable as far as location on your machine tool, and we want to also identify that on our drawing. So center lines are going to be used for that purpose. Now, the dimension itself is going to be the number with the straight lines and arrowheads on it, okay? And then we're going to have the lines that are coming down here. Those are called extension lines. Extension lines are going to come from the feature that we're interested in knowing what the dimension is of. Notice that as I zoom in here a little bit, that if this is the part outline or object lines are always going to be a thicker line weight than what our dimensions are. Remember, the object lines, when we put our layers, we set them up in AutoCAD, the object lines had the largest number for the line weight, okay? And then if you turn the line weight on, when you're using AutoCAD, you can see that those are more pronounced, okay? So the dimension lines are going to be a thinner line weight. As we look at this extension line, there is a gap between the actual feature itself and where that dimension extension line starts. Okay, always. And I look for those gaps. So when you're dimensioning, make sure that you're grabbing endpoints, and I'll show you this in AutoCAD later on. Make sure you're grabbing the endpoints of the features, because then an automatic space is going to be created, or that automatic gap will be created. You don't have to worry about placing that there. It'll automatically. But if you grab on a different part of the feature and then the dimensions extend down, and there's no gap, I'm going to be calling that to your attention. Okay, so dimensions have to have gaps off of the part. As we look here, so the center line that they were talking about, we would dimension to the center line. So we would grab the center line, and you're going to notice that then our extension lines come off that. So, and then it locates the center of that hole. Now, guidelines for using dimension and extension lines. Okay, so I'm going to zoom in here and we'll kind of see the good and the bad. So one of the rules of dimensioning is that you can cross extension lines, but you cannot cross dimension lines. So a dimension line, again, is a line with the arrowheads on it. We cannot cross those, all right? Extension lines are the lines that come off of the features. So this is all okay. We see the crossing of two extension lines here. On the next drawing over to the right, we have extension lines crossing dimension lines. All we need to do is take this dimension line that's crossing and just shift it down below so that you see the shorter dimensions, if you would, closer to the part, and the longer dimensions further away so that you don't cross them. Same thing here. We cannot cross a dimension line with arrowheads on it with an extension line. Now, you might be like, well, what's the big deal? It's kind of confusing, quite honestly. If we look back over here, we get a better picture of where we're actually going to. I would actually even take this dimension and probably put it up on top, okay? Or in a different view, all right? Just to clean it up a little bit. So if you can avoid it by putting the dimension in a different view, which makes sense first and foremost, but only cross extension lines. I will be watching for that, okay, when you dimension. It seems a little ticky-tack, but it's important, okay? And then you're going to notice over here, you don't want to do this. Notice that they don't have the extension line going all the way to the part, okay? They might be like, well, we don't want to cross those. No. You can cross extension lines. You cannot cross dimension lines. And notice, because of that gap, it's like you got to kind of line up where the dimension is going to. It's harder to see. Okay. And then the last one is never acceptable. Okay. I want everybody to look and see this one. I should see everybody's eyes up here. Okay. I don't know about virtuals. I hope your eyes are here right now. If you're not with me, come back to me right now. You're going to notice that they have dimension lines on the part. Never acceptable, ever. I don't care if somebody says to me, well, it's easier for me to do. I don't care how easy it is for you to do it. It is not to the standard. It is a violation of the standard. We never dimension on the part. You have to pull those off and away. Always. Okay, always. As we look down here, got some good dimensioning. On the right-hand side, the problem here are two dimensions. This one might not be dimensioned on the part, but it's using an object line for one of the extension lines. You can't do that. This needs to be pulled up and away. So notice you have two extension lines, two arrowheads, okay? Over on the right-hand side, same thing here. You can't use the part in order to use it as an extension line, okay? Over on the right, this is a good one. Notice that all of those values are pulled away and off of the part so that the dimensions are off. As we go to the right over here, I'm going to scooch this over just a little bit. Notice that you want to avoid the gap here because it can cause maybe confusion. So you just do the extension line over the actual part, but you want a gap to where you're dimensioning to. So avoid those gaps that we see there, the additional gaps, if you would. The next thing is arrowheads, all right? The accepted arrowheads that we have in mechanical design, according to the ANSI standard for mechanical design. Architectural tends to be more fancy, okay? They do their own thing, but we're mechanical, so we keep it simple and kind of boring, if you would. So our arrowheads are going to be this first one over on the left. You'll notice that the other ones are considered okay, all right? But I would avoid them. And the reason for that is when the arrowheads are filled in, they kind of take precedence and they're easier to see on a drawing. If they're open, it's hard to see the endpoints, and you might not think it's a big deal, but it kind of is. And the reason we used to do arrowheads not filled in, it was kind of an early CAD thing. When early CAD systems were out there, and I got the pleasure of working on those CAD systems, anything that was a digital part like this, every little bit was memory. Okay. So if you were saving this and you had filled in arrowheads, you had drawing that had, it was a bigger file than if you didn't. And at that time, disk space was kind of a premium. We had mainframe computers that we bought. We had to, make sure we had enough there. Well, now a terabyte is what? $10? Okay, or something, not that much. I don't know exactly what it is, but it's not an issue anymore. So the standard is to fill in. So err on that side. As we look at leaders are going to be, you're going to notice these bent arrows with what we call a landing, okay? The ANSI standard needs the landing on it. If you have an ISO drawing or ISO standard, they don't, but we don't practice the ISO standard. That's like other parts of the world. So we're ANSI standard. So a leader is going to be this line with an arrowhead on it, and it has a flat or a landing before the note starts. Okay, before the note starts. You're going to notice here that they see a yes and a no. Now, the problem with the no here is it's too shallow. Okay, we want our our leader line here to be between 30 and 60 degrees from either horizontal or vertical. If it gets shallow, or if it gets perfectly vertical or perfectly horizontal, it just doesn't look right. Okay, so don't do that. So keep them, at a nice distance. Just trying to make sure you don't cross over each other. So if you have another leader that you wanted to bring in here, don't cross leader lines. Okay, just they're kind of like dimension lines because they're lines with arrowheads on them. So you want to avoid crossing those. And again, you don't want them to be shallow or too steep, and you don't want them to be perfectly vertical or perfectly horizontal. All right, that's against the law. No, the rules. We'll say the rules. Dimension, scale, and dimensioning. So first and foremost, in the title block, you're going to notice that there'll always be a statement, do not scale this drawing. Now, that doesn't mean the drawing wasn't drawn to a scale. It just means that, especially when we print things off on a printer, a lot of times we're fitting it to a paper size, okay? Which means that we're not preserving, if you would, the one-to-one scale that we drew it in. We will always draw in a one-to-one scale. We'll pull our border in to fit around, which may require us to adjust the scale, okay? But we never scale a drawing that's been printed on a printer, okay? Because again, it's printed to print to size. So you don't want to take a ruler, and what that means, I don't want to take a ruler and measure something on it and then assume the dimension. No. You've got to have everything dimensioned so nobody ever has to do that. So you can't forget dimensions, or you have to try not to forget dimensions. Now you're going to know that there is a scale on the drawing, and that is what I referred to earlier. If you're always going to draw in one-to-one scale, and you're going to pull a border in to fit around that drawing, and we're going to get a lot of practice in this module doing that with AutoCAD. Okay, so then we're going to put on, okay, what was the scale of that border around the actual drawing? Okay, so we don't draw to a scale, we draw one-to-one all the time. We pull our border in to fit around, and then we put the scale of how we scaled it on that particular drawing. You're going to notice that they highlight this dimension right here. This dimension right here, it says 3.3, I think, and it has an underline underneath it. What that means in the ANSI standard is that dimension is not drawn to scale. Okay, we never do that in CAD. We never ever do that in CAD, and the reason is it's actually harder to draw something not to scale because you have to what we call fudge the dimensions, and that's again a very bad thing to do, okay? Because somebody, if they don't understand what that line underneath that means, and probably most of you didn't until I just told you, because I know the standard really well, and now you know, right? But do you think everybody on the shop floor who looks at that is going to know that? No, they're going to be like, oh, that's nice that that's underlined, or maybe that's so it was a mistake or whatever. And they're going to make it to that. And then when they draw it or when they see the part, they're going to be like, well, that doesn't look right. So always draw all of your features to the appropriate scale so that when you're dimensioning it, you are not putting anything like a line underneath saying that that's not a dimension that's to scale. We just don't do that. There's no reason in CAD to do that anymore. Do not scale the drawing. We talked about that. Directions of dimensions, values, and notes. Okay, so unidirectional dimension figures. I don't know exactly what this is going. All dimension. Oh, the notes. Okay, so you're going to notice here that all of the dimensions and the notes, the text is horizontal. Okay, we do not tip the text to go, for instance, at an angle. Notice that there's a landing here and the 7 is horizontal. We don't put it in line along there. Okay, same thing with the 30 degrees or the 7.92 to 7.87. Okay, notice the text is all horizontal. We don't tip it. Architects tip it, and that's okay. That's just their standard. Our standard is everything has to stay horizontal, okay? So be aware of that. What do you see on this drawing that is not a good practice? Anything? There's one thing I would be like, bah, nails on the chalkboard. See the radius of 35? It's on the part. That is bad business. You can have this going here, but then we would extend it out. You would have a landing and your dimensions should be out here. Okay. So just be aware that this is not a good example at all. There are some of these hanging around in the chapter. I'll point them out to you. All right. Because they are things that I would not allow. Okay. On your drawings. Yes.
So you said how we do it, we always want the dimensions horizontal.
Yes.
So then how would you dimension that?
It is. It's all horizontal. So everything you'll notice here, and that's the text. This one right here, we would in AutoCAD, we would actually select this text right here and we would just pull it, we would drag it down and over, and then the dimension would be out over here. Yeah, totally good. But you'll notice here that all of the text is horizontal, which is exactly the way it needs to be. We don't want to tip anything vertically. Okay, so that you got to turn your head, and we don't want anything at angles. So this is all appropriate here. This looks good. Oh yeah. Oh no, these are okay. These are okay. This all looks good. It's this radius of 35 being on the part. That's the bad thing here. That's the bad thing here. Yeah. Units. So our drawing borders we're always going to know what units that we're in, and our drawing boards our borders are going to identify that. So we're either going to have inch units or millimeters or metric units. All right. And that's why we have 2 different types of borders that you're going to be downloading for WCTC. So you'll always know which ones those are. So that's going to be noted on the drawing itself. All measurements are in inches unless otherwise noted, or all measurements are in millimeters as noted. And then this would be an example of we're going to be looking specifically at our title block, what our standard title block tolerances are, that any dimensions that don't have tolerances specifically to them are going to default to. So this is just one example of it's actually not how we do ours. So we'll point that out later on. Millimeter values. Millimeter values are going to be one of 2 kinds. They're either going to have no decimal in back of them or 1. Okay. And if you have 2, that's when you're getting pretty accurate. Because if you look at a millimeter is much smaller than an inch. Okay. So usually 0 nominal values, no dimension, no decimal in back of it, or 1. Okay. So if you have a drawing, you're like, I don't really see what it is. That's going to be a clue. So if you look at this is 89. There's a good chance not 89 inches. That's a pretty big part, unless you're working for like harness figure or some big operation. But if it's just a part, that fits in your hand, 89 is probably in millimeters. Okay. Now you're going to notice here that they're giving you the size of the text that we're supposed to use on a drawing. don't worry about that. We set that all up in AutoCAD and we set it up in the dimensioning manager, and we'll be doing that today a little bit later. But so we don't have to worry about that. That's gonna automatically adjust for us. Here are inch dimensions. So kind of like for the same part, we're gonna notice that most often is gonna be 2, 3 decimal places. And then if more accurate stuff is gonna be 4s and 5s if needed, depending on the tolerancing that we have. Dual dimensioning. Sometimes we can see dimensioning where there's 2 levels of dimensioning. And really what that is it's to cover the parts possibly being made in a country that is either predominantly English units like inches or predominantly millimeters like Europe and other places in the world. If you have a company where you have plants or manufacturing plants in multiple places in the world, you may see this. I worked for a company that we had exactly that. So we would have to, if our primary units were in inches, those would be the values on the top. And then we would have in parentheses or brackets below the millimeter equivalent, okay? So that's not uncommon to see dual dimensioning. In the program, we really don't do any of that, but it might be something that you see in the future. Now, dimensioning symbols. These are symbols that are going to come up and that you will be using on occasion to kind of clean up and clarify drawings. So the first one that we see here is a counterbore symbol, and it looks like a counterbore. It's just a rectangle that has an open top. Now, again, don't worry so much about the sizes here because AutoCAD has them set up, automatically for us. So if we're going to use that symbol, we're just going to select it and insert it in. The next one we see here is a spot face. So it looks just like a counterbore, except it has SF. Now, a counterbore is going to be to a specified depth with the intent of putting the head of a bolt down below the surface, as we saw. I thought it was the last time you were together or the time before. I forget. I think we looked at that. And then a spot face is just going to be cleaning up a surface. So it really is still a counterbore, but it's much more shallow. Okay. The next one is going to be a countersink. A countersink is just a V, and that's going to represent making a countersunk hole for like a flathead screw so that it sits in there nicely. The next one here is going to be the depth symbol. It's just a straight line, a horizontal line with an arrow going down. Again, we'll see examples of this, how to use these symbols and where we find them in AutoCAD. The next one that we see here is a parentheses. That's going to be a reference dimension. That's different than something not to scale. A reference dimension, when we put a parentheses around it, one of the rules of dimensioning is we can't list a dimension in more than one place on a drawing unless we give it a reference drawing for clarity in another view. Sometimes it is kind of like nice to have it there. If you have drawings that they're like a bunch of section views, and I mean, literally you could have 8 to 10 on a drawing, okay? And that's not terribly uncommon for complex parts. Well, now if you have the dimension just in one view, but then you're referencing in another view some other things where that dimension would add clarity, you don't want to put it on as another dimension. You want to put it on as a reference dimension. So that is very common, and that would be in parentheses. The next ones are arc. These aren't as common. Arc length, slope, dimension, origin. R for radius. You will see that in notes when we call out radiuses. And then the symbol for diameter is going to be a circle with a slash going through it. An S in front of it just means it's a spherical diameter. So it's kind of like it's like a ball, okay? Or like a sphere. So those are some symbols, and we'll point those out as we go along, and we'll get some practice with that. Placing and showing dimensions legibly. Okay, rules for placement of dimensions help you to dimension your drawings so that they're clear and readable. So a couple of things that we're seeing here. You're going to notice that we have 2 versions of the same part here. What they're showing is that on the left-hand side in this view right here, notice that our dimension values are staggered one to the next, okay? In the one in the middle, they're all lined up to be in the center, okay? I don't know if it's poor. It's easy to do because honestly, when you place your dimension, what AutoCAD will do is it will center it on the dimension, and then you have to manually move it over. Would I take off points for this? But this is more clear, okay? And to the standard, if you would. Okay, this is what they encourage. But I understand this. Go ahead.
Putting one on the left is the let's say we had 6 dimensions that were lined up, would they want you to kind of stair step them, or is it sort of randomly distributing? Like,
Kind of randomly, you could stairs. I mean, if, so you're saying with the next one, what if we put it in line with the 50 or the 40? That's fine. That's fine. They just don't like this so much. Yeah,
So it's more of an interpretive thing for the designer.
correct.
It was
Yeah. Yes, yes.
Specific.
There isn't a specific pattern that I'm aware of. Yeah, but yeah, I'll never mark this wrong, but just know that this is better in the eyes of the standard. Okay. Over on the right-hand side here, you're going to notice that we have hatch dimensions here, and you're going to notice that the dimension for the width there is coming off of the feature. And there's a gap for the dimension. We're not dimensioning on the feature. Neither one of these is okay. Cross this one off. It is not okay. You cannot dimension on a part. No way, no how. If I'm pointing them out right now because you need to do everything you can to avoid that. Okay. You'll usually not convince me. You'll be able to find a place off of that drawing in a different view or someplace else to put it. And sometimes students will say, well, then I have to make another view. Yeah, you do that once. You do the extra view once. That part's going to be made potentially thousands of times and interpreted. Okay, so we want to do it the right way. Over on the left, these are good. Okay, no crossing dimension lines, and all of them are off the part. Over on the right, bad business. This is like minus 432 points off your grade. No, just kidding. Don't do it. Like I said, you will see it on an industry too. It's awful. It's terrible. Nails on the chalkboard. You're going to be my little minions out there correcting all the bad stuff. Okay. All right. This is talking about text type. Don't worry so much about that. We will set that up in the dimensioning manager that we have in AutoCAD, which is really nice when you're doing it, using CAD software. Let me zoom out here a little bit. Placing and showing legibly or dimensions legibly continued. Oh, here's up here. We're going to zoom in on this one. We never dimension to hidden features, and we only dimension to features where we see them as their true size and shape. So if something is a hole, a circular hole, we dimension it where we see it as a circle or where we can get object lines. Okay. We just got done talking about section views. And I had said to you, the reason we do section views, although we're not doing it yet, is so we can dimension to visible lines and not to hidden lines. Over here on the right-hand side, illegal. Every one of these dimensions is going to a hidden feature. You cannot do that. Okay. You have to create, in this case, a section view so I can see those internal lines as object lines, visible lines, and now I can dimension to them. Okay. The preferred place for diameters also is going to be where they're circles, but depths, are good here. The next one that we see here over on the left-hand side compared to the right-hand side. Let's look. Over on the right-hand side, you're going to notice that we have radiuses and diameters. Oopsie, I'm going to zoom in, sorry. Radius and diameters in the view that we see them as their true size and shape. So the diameter of the hole, diameter of 22, okay? The radius of, that arc going over the top, radius of 34. Where the location of that hole is, it's on center here, but it's 54 up from the bottom, okay? We wouldn't put it over here on this side because this is a hidden feature representing that hole. The center line is going through here, but you might say, well, why can't I dimension to that center line? Essentially, that center line is dimensioning to a hidden feature. You can't dimension to a hidden feature. So you can't dimension to the center line of a hidden feature, okay? So all of this is all good. Over on the right-hand side, couple things here. First of all, you're going to notice the hole. We don't see the dimension here where we see it as a circle. We see it up here where it's pointing to a line that's a hidden line. Okay. Yeah, that's the hidden line for the circle. But number one, we can't dimension to a hidden line. And number two, we're not seeing it in the view where we see the circle as its true size and shape. Okay. So we always want to default here. Okay. What else do we have? Oh, here, you're going to notice that we have this cutout. So we have 28 wide. If we go up to the other view, we have the 28 wide right here. This is where we can see that it's an actual cutout and what the depth is. This is the true size and shape of that cutout view. Do you agree? Yes, these are tangent lines, but up here is the better place to put it. Okay. Radius of 34. Yep, from the center line to the outside, there is a radius, but here's where I see the radius. It doesn't make a lot of sense there. Okay. These are the types of dimensions over on the right-hand side. Not so much in AutoCAD because we have to manually place our dimensions. So you guys have control over that up in front, up in the beginning here. But as you progress in the program to, for instance, SolidWorks, we create the model, and then I'm going to say this in quotes, we can automatically create and place dimensions, or SolidWorks will place dimensions for us. It'll do stuff like this. You have to clean those drawings up, okay? Because yes, they're just putting them on. They're a machine. You are the designer, you are the human, and you are going to do the right thing. Does that make sense? Okay. And when I'm having the students dimension, they'll be like, oh, well, that's how SolidWorks did it. I'm like, SolidWorks isn't the person. So they have to clean those up. Yes.
Good example, the 14 for the center line is on there. That's acceptable, even though it's.
It is. It's technically not to the hidden line. I would interpret this as a center plane that is down the part. And so that's like the center plane, if you would, of that cutout. So that one I believe is okay. I'm interpreting that as a center plane extension off of that center line, which happens to also be in the middle of the part. Yeah, good question. So Deborah was asking, is the 14 over here okay? Because it's coming off of a center line. Technically, I would call that a center plane of a non-cylindrical feature of size, which is kind of that bottom portion there. So, okay. And again, these are, places that you can go back to as well. I'm not expecting you guys to remember all these rules, but I want you to kind of see these applications so that when you're picking it out and trying to decide, you have chapter 11 to go back to. Okay. Let's look at what we have here. Oh, so here, this is what we would call double dimensioning, okay? It's just a term for you have too many dimensions on things, and it might be in the sense of actually putting a dimension in two places on a drawing or over dimensioning something. So let's look at what we have here. So you're going to notice up in this view right here, we've got a 12-inch wide part or 12 millimeter wide part, okay? They show this 12 millimeters in the right view, and they also show it up in the top view. And notice neither one of those has the parentheses for a reference around it. This is called double dimensioning. Which one is right? The problem with this is that in the event you change this drawing, the thickness changes. There's a good chance you're not going to see it in both places. And then all of a sudden, you have a part out there that's going to have a dimension that's different in two different views, and somebody's going to make it to the wrong dimension. Okay. So make sure that you never double dimension. And if you do add a dimension in another view, make sure that whatever the second or third version of that dimension is, it has parentheses around it so that it's identified as a reference dimension. Okay. Over on the right-hand side here, the one in the middle, you're going to notice that we have an overall dimension of 2.86. Then we have a distance of 0.32 or 0.62, 1.62, and then they've got a 0.62 over here, but they have it crossed off, okay? And the reason for that is it's really tolerancing, okay? We have to pick one way or the other. You could either have 3 individual lengths here without an overall, or if we have the overall, we can't have all 3. The reason being, as I stated earlier, and we'll understand this more in our next module about tolerancing, but each one of these has a tolerance on it. It would default to the title block because we don't have a tolerance specifically in back of it. So what you end up having is, let's say a 2-place decimal is plus or minus 20 thousandths. That's 20 thousandths, 20 thousandths, 40 thousandths, 60 thousandths total when I add these 3 up. But then when I look at this bottom dimension, that's one dimension. That only has 20 thousandths on it. Which one's right? Okay, that's the problem with it, okay, because it doesn't add up tolerance-wise. So you as a designer would then decide what are the important dimensions. They might be the 3 that are stacked here, and we would leave those alone without an overall. Or you would make one of these reference, okay? You would make one of them reference. Maybe it's the overall, maybe it's one of the other ones, or take one off, okay? And then that's how you solve that. Same thing here. You're going to notice that you have 1.24 on one side for the overall height. And then you have these 2 dimensions here. You have to pick. You either get rid of one of these or you make one reference, okay? Oh, in this case, for an angle, you would have to omit one of the dimensions that we see here. So by the angle where it starts at the 41.2, it is going to create the depth that we see here, okay? Because of the other dimension as well that's down at the bottom. You would have to either use the 12.7 or the 60 degrees. You as the designer would know which one is more important or which one takes precedence, okay? As we look here, you're going to notice that they cross out all three of these. And the reason they're doing that is because the outside diameter of what would be considered a cylindrical feature would be an outside diameter of 46. They should have the diameter symbol in front of there because this is calling out the outside diameter of a cylindrical feature. Cylinders, so that's an external cylindrical feature. We do dimension in the view that we see it as a rectangle, if you would, okay? Because then it looks more like an outside diameter. You wouldn't dimension it precedence-wise where we see it as a circle. That is, I'm not going to call it an exception, but it's the rule for external cylindrical features. When we have an internal hole like we see here, then we show the diameter of 20 pointing to the hole. You would not show it over on the left-hand side, dimension to hidden features, first of all, and you wouldn't show then the distances from the edge of this part because we would locate the center of the cylindrical feature to share the same center as the outside diameter. On the one in the middle here, you're going to notice that all of those corners are a radius of 0.5. You don't call them out separately. You call out one of them and you put however many instances in front. So in this case, 4 by radius of 0.5. What else do you notice wrong about this part? What was that?
On the inside.
Yeah, it's a dimensioning on the inside or on the part. You gotta push that up in a way, right? Push it up in a way. So that's bad, but what they're trying to show here is to use the 4 by, tell us how many there are. And then we see the one down here. What do we got here? Oh, 2 by a diameter of 50. So there's a hole that has a 50 diameter here and here. They're both the same size. Do not dimension those separately, okay, as their own. So that's what they're showing in this case. And then you're going to notice that the boss, I'll call it, or the external cylindrical feature, 1 inch diameter here, that's going to be dimensioned on where we see it, if you would, as the rectangular view and not on the outside here. If you would do this, you say to me, is that the worst thing in the world? No, I would much rather you do that, dimension an external feature in the cylindrical view than ever put a dimension on a drawing or on a view. Does that make sense? On the part. So those are things that are better than others. Some more double dimensioning examples. I'm not going to go through each and every one of these, but you'll notice here that first of all, you never dimension on the part itself. But if you show a dimension in a circular view, you can't then show it in the rectangular view. That would be double dimensioning. Okay. And so on. So a couple other examples. Dimensioning arcs, fillets, and rounds. So we've already created rounds and fillets using AutoCAD software. Okay, that's where we make a sharp corner rounded. Okay, that's either a fillet if it's an inside corner or a round if it's an outside corner. And then we've created arcs as well. So there are a number of ways that we can dimension fillets, rounds, and arcs. And we can see them here. I think there are some examples, but we can definitely highlight that. You can also add a general note, okay, on a drawing. So for instance, fillets are a radius of 6 and rounds are a radius of 3 unless otherwise specified. And it can be a general note on the actual drawing. And then it avoids having to dimension each and every one of these, okay? And that's very common for parts that have the same radiuses. And I think we've seen that in a couple examples where you've been doing the drawings and you're looking. I think I had a question or two like, what is this radius supposed to be? And then there's a little note telling you, what the radiuses should be. We can add those as what we call general notes to drawings as well. So size dimensions on cylindrical features. So first of all, the diameter symbol is going to let us know that something is a circular feature. So showing the diameter of 158 millimeters here and 80 millimeters on those external cylindrical features in the rectangular view is completely acceptable and actually the preferred method than putting it over here in the circular view. Over on the right-hand side, you see these all having the diameter, but what rule are they violating?
Dimensions are vertical.
Right. So Carlos said the dimensions are vertical here. We got to turn our head, if you would, to see them. They all need to be horizontal, and then we would stagger their values. Okay. One to the next. This is acceptable in ISO standard. ISO is International Standards Organization, and they kind of oversee, if you would, everywhere else except Canada and America. Okay. So so you may see those if you are getting prints from companies from around the world. Okay. So they just operate underneath a little bit different standard than we do. Diameter symbols. Okay. So, oh, and as you can see, there's some things on the part, which is bad. Not good. You guys cannot do those. You are held to a higher standard. All right. If we look here, size dimensions for holes. So we're going to find in AutoCAD, there's going to be a hole dimension, a radius dimension specific. So when you click on that dimension and you click the outside of the hole, it's automatically going to dimension for us what the size is. So, so we'll be seeing these. You'll notice here that we have good dimensioning. When we show a hole size, and dimensions will automatically do this, you are going to click on the hole and it'll automatically place that dimension line so that if we extend it, it's going to go through the center of that hole. We do not want anything looking like this. If I see this on a drawing on the right-hand side, I will know you did not use the dimension command to put those in. Those would have been like leader lines or notes, okay? And you'll notice that if I extend that, further, it's not going to go through the center. So these are the correct ways to put it, not at all like this, okay? This, like I said, I know right away, did you use the radius dimension and did you use the hole dimension? Okay, because it'll automatically do it for us in AutoCAD. Here are some other notes, and we're going to look more specifically at things like this. This is a spot face, countersink, and threaded features. Dimensioning counterbores and spot faces. This is utilizing, we're going to see the symbols come in play here. So this is a diameter of 6 through. That's the smaller hole going all the way through. That would be like, if you would, the body of a fastener going through there. And then the counterbore is going to seat the head of that fastener. And you're going to notice that underneath we see the counterbore symbol. This is that rectangle with an open top, kind of looking like a counterbore. And that's a diameter of 10. So that's going to be the distance across here. And it's going to be, oh, a radius of 1 down here. Gross. Okay. I've never seen that. Usually you see it in, they're dimensioning it down here. So that's okay, I guess. That's okay. But I've never seen that before. And then you're going to notice that we have a depth dimension, and that's going to be how deep that counterbore is going to be. So the radius down here is an R1, not typically the way you see it all in one note. I probably wouldn't see the R1 there, but then you would add it as a dimension in a different view. So, so something to consider. And then you're going to see the spot face version here with an R1 in back of it. Again, that radius is at the bottom there. I think that's okay, but better to see it in the view so you know where that radius comes from. Because here, because it's not typical, could that radius be on the top here, or could it be on the bottom? It's kind of hard to, it's hard to know without actually specifying it. So better to specify it in that case. Dimensioning curves. Here are some ideas for dimensioning curves. We'll see maybe some things like this, but these are valid ways to show it, just making sure that we're not putting them on the part, pulling them away. Dimensioning rounded end features, things like slots, for instance. Okay, so we're going to notice here that as far as the overall length of a slot, yeah, that's fine. As far as the overall length of a slot, you can either go to the edges of the radii, or you can dimension to, let me see over on the left-hand side, to the center lines. See, let's look here, the center lines of each one of those. It really speaks most specifically to how that part is going to be made and how it's going to function in the end. So if the overall length of the slot is more important to you, then that's how you would dimension. If you're going to be making it, you want to locate the center of the tool that's going to put that slot in place, well, then you're going to, put the centers in there. Okay, so it just kind of depends on how both are acceptable ways of dimensioning a slot, but otherwise it would be, one or the other. Dimensioning threads. We're going to be looking at fasteners and threaded features more specifically in our next unit. So we'll be covering this more in detail then, but you're going to notice here that when we call out fasteners, the holes are going to look a little different. In the circular view, we're going to see a hole that is going to be an object line in the middle. I'm going to zoom in here so we can see that. Okay. And then you're going to see a dotted or hidden line circle around the outside. That is representing the threads that are going through. Okay. So in the circular view, we're going to see it as two circles, one object line in the middle, hidden line on the outside. And then in the side view, we'll either see it in what we call the schematic view here or a simplified view. We'll also see versions of that, and both can be accomplished in AutoCAD or other softwares as well. The call out for the threads that we see here. This one has a 2-line call out. This is kind of an older way of specifying a threaded hole. The top line is what we call the drill, the tap drill size. And this is going to be the equivalent of the inside or the minor diameter of the threads. Okay. And it's telling us how far that's going to go down. And that's going to be, if you look, that's going to be the smaller diameter that we see here at the bottom. Okay. And it's telling us that's going down 0.44 inches. And then the second line is going to be the call out for the actual thread. So this is a 1/4 inch thread, 20 pitch, which is a coarse thread. So UNC. 2B just means that it's in an internal right-handed thread, and then it's giving us the depth. We will be learning more about this call out the next time we're together, but that's a call out for a threaded feature. Okay. Knurling. Knurling is going to be like a rough surface that we intentionally put on. And usually it's going to be like on hand tools. It's going to be a rough surface so that where you're grabbing onto it, you get a little bit more of a grip rather than a slippery surface if you're going to be tightening down on something. Or in this case, it's like a knob so that we can, move it or such. So those are some examples of a little bit different types of features. Another type of feature is a chamfer. A chamfer is when we kind of break the edge, a sharp edge on a feature. Many times it could be on the end of a cylindrical feature as we see here, or on the end of a non-cylindrical feature. And it's just breaking off the corner. Sometimes if we anticipate like handling the part with your hands, the parts can be very sharp otherwise. So putting a chamfer on, it can also serve as a lead-in if it's going to fit into something else. So, so this would be a typical call out for a chamfer, or a couple different ways that you can call it out. We'll talk about those as they come up as well in drawings that we do. Dimensioning keyways or key seats. Keyways and key seats are specific items that are going to transfer torque when we're rotating an object. And a key can take a couple different forms. Okay, it can be just a rectangular key that sits down in a seat, and then it goes up above, and then it's going to go into a keyway in like a bore in this case. Not something that we're going to be terribly worried about in the near future, but you will come across these, as you kind of go through the program and such. So I'm not going to spend a whole lot of time there. Locational dimensions. Locational dimensions are dimensions that are going to locate what we call different features of size. And it's basically letting us know from one feature to another how they're relative to each other. So for instance, in the top view here, we can see 2 holes, and we're dimensioning the distance between those 2 holes on center. So we're dimensioning the location of one hole with relationship to the center line of another hole. Okay. If we wanted to know what its vertical distance is, we would locate it from one side of the part to its center line, for instance, going vertically, okay? And those would be locational dimensions. Couple different ways that we can call out bolt circles. So a bolt circle, for instance, is going to be a circle for which we locate a number of circular features. We see this a lot on, as you can see, a circular feature like this that might be an adapter plate where we have fasteners going through, and it's going to then, butt up against or mate with another feature. So you would call out the size of the center circle here, okay, for which, and we call that a bolt circle, for which all of those share, and they're on the same bolt circle. And then you would just say that those are whatever size they are, evenly spaced on that bolt circle. Another way you can call it out, if they're not evenly spaced, you can put dimensions like angles between them, or you can call them out so that you have the, if you would, X and Y locations from the center of the part. So a couple different ways that we can call those out. Getting towards the end here. These are called coordinate or ordinate or baseline dimensions. As we look at this part, this is the one exclusion or exception to horizontal dimensions. You're going to notice here that on this part, up in the upper left-hand corner, we have what we call the origin or the 0, 0, okay? And then as we go from that 0 and we go down, what we're given is the coordinate in this case, the vertical or in the Y direction that this hole or these series of holes are from the top of the part. And then you can continue down from the top of the part to the next set of holes and so on, okay? If you would, that would be a Y coordinate, right? If we go horizontally, you're going to notice that these dimensions are tipped up. Again, this is the one exception. If you are doing ordinate or coordinate or baseline dimensioning, however you want to call it, those all mean the same thing. You can do this, and it'll set it up like this in AutoCAD, okay? And here from the vertical face, but in an X direction, these are going to be the coordinates of where those would be located, okay? So this is another type of dimensioning scheme that you can use. This is really nice when you have, let's say, a big plate. You're going to be putting a whole bunch of holes on it. And if you're going to be programming that with a CNC machine, the operators are really going to love you because now you've figured out all their dimensions for them, okay, that they're going to take from a 0, 0. So if it makes sense, you want to think about that. So that's one of those like manufacturing processes, types of applications that, you can use and make your dimensioning match that. You can also create families of parts. So a lot of times we have a similar part, but we're just going to make it different sizes, kind of like fasteners, right? They have the same size head, but maybe the length of the body is different. So what you can do is you can identify the drawing. Okay, you're going to draw one of them. You're going to identify each one of the dimensions with a letter, and then you're going to have a table that is going to then identify what the dimensions would be for different sizes. Okay, so that's very common to do as well, especially for like purchase parts. Dimensioning for numerical controlled machines, as we talked about earlier, this is where we can find if we're not going to use ordinate dimensioning, you're going to notice that a lot of times it's all going to come from one corner and all the dimensions. So this would be, another way that here's in this upper right-hand corner, notice all of the vertical dimensions are coming from that top surface, and all of the horizontal dimensions are coming from the right side vertical surface. Okay. So again, giving you, if you would, the coordinates, not in the baseline or the ordinate dimensioning, but in this case, finding a common place and then identifying the locations, X and Y coordinates for that. And then the last one here, this is a machine pattern or forged drawings. I'm using this for a little bit different example. As you can see here, if I zoom in and I look at, oopsie. And I look, oh, this isn't the last. I think we're getting close to the end. But you're going to notice here that as we look, there's a lot of violations to the standard here. We've got a lot of dimensions on the part, and you can see how confusing this can be. First of all, the first thing I would do for this drawing is put it on a larger border, and in some cases, create multiple sheets for that same one so that you can then, be able to kind of see what's going on here a little bit better. So way too crowded. See what else we got here. Sheet metal bends and radiuses here too. There are standards on what we're going to be using or what we're able to use for an inside radius, outside radius based on the thickness. We're not going to be doing a lot with sheet metal parts, but you know, here are some guidelines there. And then I think this is lastly adding notes. Notes are going to be added using leader lines. A leader line is going to be a line that has an arrowhead on it and then is going to identify a note or some information that you want to relay. The same rules for adding diameters and radiuses apply here. So notice that the leaders are at ideally between 30 and 60 degrees, okay? We're never going to have a vertical or a horizontal leader for a note, and we don't want it too shallow or too steep, okay? So you gotta kind of find where it looks good. So, so here are some good examples of that. And I think that is our last slide. So really the purpose of this lecture was not so much to, you know, get all the rules in your head right away, but to kind of show you that chapter 11 gives a lot of good information of the application of dimensionings, but then also some shortcomings as well. So probably the first one being we never want to dimension on the part, which they kind of violated quite a bit, but we identified most all of those. Okay, so I am going to stop our recording here.